SwayamPrabha. Digital India. Educated India.
In this lecture, we'll be studying how we can reduce the closed-loop tracking error of the closed-loop control system. Before we proceed, I'd like to refer the combined error equation what we derived in the last lecture. So let me rewrite the equation. ER is equal to 1 upon 1 plus G naught of S RS plus G naught of S 1 plus G naught of S WS minus GP of S 1 plus G naught of S MD S. Also, you can write this expression, write ER of S plus EWS plus EMDS. So ER basically the tracking error due to the reference signal, EWS the tracking error with respect to the measurement noise, EMDS the tracking error due to the disturbance to the system. And also we have, as we mentioned in the last lecture, the reference signal, the reference signal and disturbance signal are slowly varying with time, or you can say it has low frequency content. And the disturbance, the measurement noise signal, the measurement noise signal, basically the measurement noise basically varies with time very fast. Right? A fast varying signal, we can say fast varying signal, or we can say it has high frequency content. Now we'll look step by step how we can reduce the tracking error with respect to reference signal, tracking error with respect to measurement noise, tracking error with respect to disturbance. So first, let's move with the reference signal tracking. Reference signal tracking. From equation, let me write this the equation number. This is the equation number 1. From equation 1, we can write from equation 1, we can write ERS equal to 1 upon 1 plus G naught of S and in frequency domain, we will put substitute S equal to J omega. We can write ER J omega equal to 1 by 1 plus G naught J omega R of J omega. And if you write in magnitude form, we can write ER J omega magnitude 1 upon 1 plus G naught J omega and R J omega. If you notice from this equation, if you want to reduce your j omega, this term should be very low value. Once it is very low, then we can track the reference signal. So we can write for good reference signal tracking, we should have as a control engineer, we should be very careful that the error in the system should be zero. That is our main motivation. And based on this motivation, we are doing all these practices. We should have 1 by 1 plus g naught, g, g naught, j omega should be very, very low value. For this, if you notice, to satisfy this condition, we should have for this, we need to have g naught, j omega should be very high value. Since g naught basically the open loop transfer function with the unit feedback, so we can write gp j omega, gc j omega. If it is unity feedback, this is basically open loop transfer function. And it is obvious that the GP of is basically the natural system. We can't change anything in this transfer function. And only we can play here. So we can change the GC, the control algorithm. To satisfy this condition, we should have GC j omega should be very, very high value. So once we satisfy this condition, we can track the reference signal. Now let's look the disturbance rejection. How can we reject the disturbance into the system? Rejection. From equation 1, we can write E MD is equal to, we can write GP of is 1 plus G naught is MD S. And already have mentioned the disturbance are slowly varying signal. If we write this equation in frequency domain, we can write E MD j omega equal to, this is should be minus GP j omega 1 plus G naught j omega MD j omega for good external disturbance rejection. We should have if you want to minimize this disturbance, error due to the disturbance, so this part should be very, very low value. So we can write, we should have ED, EMD, j omega, the magnitude equal to GP j omega 1 plus G naught j omega MD j omega should be very, very low in the range. So this condition will valid in low frequency range. So we can write over, this should be very low value over the low frequency signals. So we can write for good reference signal, reference tracking, we have already taken GC omega should be very high value. That is already I mentioned here in this part. And for the low frequency range. Now you can write GPG omega 1 plus G naught J omega should be, we can write, since this is a very high value compared to the GP, we can write from this expression, we can write GP J omega G naught J omega, or we can write 1 up by GC J omega, this expression. Again, from this equation, we can say that the above equation suggests that we need to have GCG omega should be large in the low frequency range for good reference signal tracking and disturbance rejection. So as you mentioned before that the reference signal and disturbance signal are low frequency, they have the low frequency content, and we can reject the error due to the reference signal and error due to the disturbance once we have the controller gain is very high. Now we'll look the how we can attenuate the measurement noise. Measurement noise attenuation. From equation 1, the tracking error due to measurement noise is EWS equal to G naught of S 1 plus G naught of S WS. And in frequency domain, we can write EW J omega equal to G naught J omega 1 plus G naught J omega W J omega. And then in the magnitude, we can write EW J omega G naught J omega 1 plus G naught J omega W J omega. For good measurement noise attenuation, From this equation, we can write for input measurement noise attenuation, we should have this term should be very low value. This term should be very low value. So we can write G naught J omega 1 plus G naught J omega WJ omega should be very low in magnitude. In the high frequency range. So this is how we can tackle the measurement noise in the system. So to accomplish this, we should have to accomplish this condition. We should have we should have G naught J omega should be very, very low in magnitude at high frequency range. So this is how we can tackle the combined error in the system, and we can fulfill our mission objective, or we can track the desired reference signal. Now we'd like to take the total control effort in the system. The closed loop control effort in the closed loop system, the closed loop control effort in the control system. Let's rewrite the equation we had. The total control effort in the closed loop system. From the previous lecture, we have derived that equation. U of S equal to GC of S and EMS. So let me, if you have some still confusion, let me write the block diagram. We have, this is our R of S, and we have controller GC of S, and we have disturbance signal to the system, MDS. This is the plant, GP of S. This is Y of S. And we are measurement noise coming to the system, which is WS. And we have feedback here plus, and this is YEMS. This is EMS. And this is U of S. So from this figure, we can write the U of S, we can write GC of S into EMS. And if you, EMS already we have derived in the last lecture, please follow. So we can write GC of S 1 plus G naught of S R of S plus minus GC of S 1 plus G naught of S WS and plus minus G naught of S 1 plus G naught of S MDS. Let me write some note here. How can proceed further? Note. In the aircraft system, we have many actuators in the system. And based on the control input to the actuator will respond to the system. So any real actuator, any real actuator has limitation in the amount of control effort that can be applied to the system. Therefore, we can write the control law should be designed in such a way that to avoid the control signal from becoming too large. So this is very important point while designing the control system for the dynamical system to be controlled. And also we have seen that for good reference signal tracking and disturbance rejection, the open loop gain should be very large. It means G naught, J omega should be very, very large for low frequency, and for measurement noise attenuation, noise attenuation, the open loop gain should be very small in high frequencies. So we can write G naught, J omega should be very small in high frequencies. So based on this condition, we'll be going to how we can look the control effort in the open loop system. So first, let's large open loop gain. One is if the open loop gain is very large open loop gain. Open loop gain which is G naught J omega we find, let me denote this equation number 2. We find from equation 2, so we are having 3 different components: the control effort due to the reference signal, control effort due to the measurement noise, and control effort due to the disturbance to the system. So we can write the control effort your J omega equal to G naught J omega 1 plus G naught J omega or J omega, which is equivalent, we can write Gc J omega and G naught J omega to R J omega, or you can write 1 upon Gp j omega or j omega. This is the final expression we're getting from this equation. So here, let me denote this equation number 3. And if you write the control effort due to the disturbance, umd j omega equal to g naught j omega divided by 1 plus g naught j omega into md j omega. We can write equivalently md j omega. Let us write this equation number 4. So this condition we are getting the final expression based on this condition basically for the large gain. So these are the equation we're getting. And if you write the total control effort due to the measurement noise, UW j omega, total magnitude of the GC j omega, 1 plus G naught j omega, W j omega. And for the large gain, we can write equivalently GC j omega divided by G naught j omega, W j omega, or you can write 1 by GP j omega into W j omega. And let me denote this equation number 5. It is clear from equation 3 and 5. It is clear from equation 3 and 5. The control effort can be very large if the plant gain, basically here, if you notice, here we have the equation 3 and equation 5, the total control effort are expressed in terms of plant gain. This is basically plant transfer function. And the magnitude of this basically plant gain, the plant gain is very small. While the open loop gain, G naught j omega, is very, very large. So therefore, we should try to avoid the situation where the open loop bandwidth is significantly larger than the plant bandwidth. So we can write, we should try to avoid the situation where the open loop bandwidth is significantly larger than the plant bandwidth. So this part we should be, we should keep in mind while designing the autopilot part, while designing the autopilot for the aircraft system. This is a very, very important point. Now let's look the small open loop gain. So there is two conditions we have discussed in the combined error tracking. One is high gain, another is the low gain. Now we'll look how the small open loop gain going to be affected in total control effort. Small open loop gain. As you mentioned, the measurement noise typically has primarily high frequency content, and we try to make the open loop gain very small over those frequencies. Basically, this is the condition we have already derived. It should be very small for the over the frequencies, high frequencies. So we can write for small open loop gains G naught J omega should be very, very small. We find the following from equation 2. So for the small gain, let's look how the total control effort due to the reference signal, due to the measurement noise, and due to the disturbance. So we can write U r J omega GC J omega 1 plus G naught J omega R J omega. It's equivalent, we can write. Since here this part is very, very small, we can ignore this part. We can write GC J omega for the small gain of the open loop transfer function or J omega. Let me denote this equation number 6. And total control effort due to the measurement noise UW J omega, we can write GC J omega 1 plus G naught J omega W J omega, which is equivalently for small open loop gain. We can write GC J omega W J omega. And let me denote this equation number 7. And if you look at the disturbance part, UMD J omega, we can write G naught J omega 1 plus G naught J omega MD J omega, or equivalent you can write G naught J omega and so let me denote this equation number 8. Based on this derivations, let me write note from equation 7, because in the previous case we are looking at this part and this part. So now we'll look the control effort due to the measurement noise for the small open loop gain from equation 7. It is clear that not only should the open loop gain be very small, where G naught J omega should be very small at high frequencies, but the control effort or the control gain should also be very small, which is GC G omega should be very, very small to avoid unnecessary control shattering, which resulting from the measurement noise. This 2-4 is very, very important, how we should choose the gain in the system while designing the autopilot for the dynamical system. Let's stop it here. Basically, these are the conditions we have to follow while designing autopilot for the dynamical system. In the next lecture, we'll be going through some basic design procedure in the frequency domain. And before that, we'll come up some concept of phase margin and gain margin and how we can compute for those margins from the magnitude and phase plot. Then we'll go to some example autopilot design for the aircraft system. Thank you very much.